and thanks for joining us. My name's Darlin. I'm chairman of the BCS Central London and North London branches, and we have got another great event for you, another webinar, but we will get to the stage where we start having live meetings again when enough people want to come and join us at them. Meanwhile, you know, we've got food on our minds, of course, but we've got other things as well. I just want to share with you a couple of colors, yellow and blue. Yellow and blue are very much the colors that are on my mind today, and I think you may know the reason why. In view of global events. Iain has also tailored his screen, I notice. His chips and everything screen features the colors yellow and blue in a slightly different context, but again with global implications. So today we're talking about chips with everything, sure. Semiconductors, everything from supply to sustainability. Well, you know it from the news, and you know you've got loads of chips in your home. Maybe one on your shoulder, I don't know, but have I got one? No, I think I left mine somewhere else. But we are facing a huge glut of chips and the need for chips, aren't we? In numerous devices and in major industries, millions of products, cars, washing machines, smartphones, and lots more rely on these chips, also known as semiconductors. Now, our presenter, Iain, knows rather more than most about semiconductors because he's the CTO of Intel UK. He's also very much a friend of ours and of the BCS. He's a fellow of the BCS. In terms of his day job, he's got over 15 years of leadership and management experience and almost 30 years of technology industry sales insights. And that spans numerous industries. I find it hard to believe you, having a look at your youthful face there, but I'll believe you. He's currently CTO and Enterprise Sales Director for the UK at Intel, and he also represents Intel on the cloud leadership community for Tech UK. Please join me in welcoming Iain Beckingham.
Lovely, thank you, Dalem, and it's a pleasure to be here, albeit a shame that it's not in person. I'm sure maybe I could have splashed out for some chips for the food at the end. Actually, I think the canapes and the wine are a little bit better. Look, it's a great privilege to talk to you all today. You know, if anybody's attended the stuff in person, I normally fly a drone around or find an excuse to. I'm not going to do that. It's probably a little bit awkward doing it virtually. But what I do really like and appreciate is just some questions. I'm quite happy to, you know, not bother with the slides, quite honestly, and just take questions or just have a conversation, or we just use these as a conversation stimulant. Okay. And basically, you know, we looked at the title and it's like, okay, chips with everything, and we can kind of go anywhere. I'm quite happy to take questions on any subject. I may give you the Intel corporate line, or I may just go, look, this is my personal view. I'm good to do both. Try and keep it interactive. I can only see my screen at the moment. So if there's some thumbs up, thumbs down, or you want me to move a little bit quicker, or you got Q&A, I know there's the chat box, so we can do it that way as well. I am going to try and share some videos. I'm not sure whether that's going to work or not, but we'll give it a go. And if it doesn't work, just let me know and we'll move on. So one of the questions I always get when I go and see customers is, you guys are just chip heads. And that's all you do, isn't it? You just make chips. And what I just wanted to give you guys out there was actually, yes, we do make chips, right? And we do a fabulous job of it, if I may say so myself. But actually Intel has been around for 50 years. If you recall the 4004, which was one of the first microprocessors that had its 50th anniversary just last year. And what I also wanted to talk around was, actually, if you look at Intel, it's got a big history of innovation. So we were founded in '68, and I'm sure some of you will know who founded us, and if you can put it in the chat, then I normally do prizes as well, right? But I don't know how I'm going to do prizes. Maybe I'll have one prize and I'll figure out how I send that to the person. So founded in '68, as you can see there, we got the 4004, so that was 50 years old, right? And you know, this was a processor. Sorry, was there a question?
Yeah, Gordon Moore, is that the right answer?
Gordon Moore, perfect.
Watch Tech,
Very
you're the winner.
Excellent. So Gordon Moore, Robert Noyce, Andy Grove, the three. Although, yeah, I think that was correct. So 4004, really designed to go into a calculator. Actually, that's what it was kind of built for. And Intel, you know, kind of dabbled a little bit with memory controllers and stuff like that. But really, I think what we're really known for is kind of that breakthrough with IBM in 1981, which was the beginning of the PC. The other thing that people don't actually realize that I think we did was, you know, co-founder of Ethernet. And we've been involved in Ethernet for a very long time. Moving forward, I'm sure some of you are familiar with the 486. I kind of joined around, it's not quite on here, around 96 into Intel. I had the first Pentium 200 megahertz in the lab with MMX technology. And what I kind of joined for was to do essentially kind of what we're doing now, right, which is video. But at that time we didn't have, well, we had the internet, but we didn't have, you know, the internet was typically a dial-up, right? So it was very low speeds, and my first project was doing a modem to modem connection and sending video and voice over it. I mean, we take it for granted these days, right? As you can see, Intel's revenue continues to grow along the bottom. We came out with USB. I remember some of the first things around USB, and you know, now I look at my home and I've got USB sockets as part of my electricity socket, right? So it's a technology that's really taken off. For those who remember Centrino, that was our first dabble into essentially a laptop technology, but it had the built-in Wi-Fi. And around that time, again, we take it for granted these days, we had Wi-Fi hotspots. I was saying Hi-Fi there. Wi-Fi hotspots springing up, right? And now again, I think we've kind of just, you know, that technology. It's been around 16 years. Everybody has that thinner light laptop. We kind of expect more and more battery life. We do gaming on these devices, right? And we expect ubiquitous connectivity. So 50-year anniversary a couple of years back, and we're still innovating. And this is the exciting thing about Intel, right? Is, you know, everything from the manufacturing perspective to some of the connectivity features like Thunderbolt, to things like 5G, vRAN, ORAN, AI. You know, there's just a ton of stuff happening. So if there's one thing perhaps you take out of this session, Intel does a little bit more than just chips. Here's a few other things that, you know, and I've talked to some of these things, and I kind of look at it in this way. You can't just make fantastic hardware. You have to really have the software that goes and takes advantage of the hardware as well. As a question for the poll, maybe somebody could have a stab at, and I'll try and frame it a little bit. most of the people that work at Intel are probably in the fabs, right? The manufacturing facilities. But we're a hardware company. But how many software engineers do you think we have? And maybe I can get some responses there. I can't see the responses, so.
20,000?
Oh, that's a perfect guess, actually.
Maybe they
Is
Googled it.
somebody an insider here?
Watch Tech.
Very good. So 20,000 people working on software. Again, a couple of stats that people perhaps know, perhaps don't know, but number one contributor to the Linux kernel. 100 different operating systems that we optimize for. You can kind of see all the standards, you know, and the standard bodies that we attend, everything from 5G, 6G, CXL, which is the interconnects on the CPUs, Wi-Fi, USB, floating point, DDR. You know, technology has never been, I think, more important to humanity. And what we're seeing is there is a drive for exponential computing. And this is part of the challenge that we've got today, right? Which is everybody knows there's a chip shortage, and how do we keep up? Part of what's driving this is everybody is on their digital transformation. And if you kind of look at that, the underlying technology powering the digitalization of everything is being accelerated by what Pat Gelsinger, who's our CEO, calls the 4 superpowers. And those 4 superpowers are ubiquitous compute, pervasive connectivity, cloud to edge infrastructure, and artificial intelligence. Each are probably impressive on their own, but together, the superpowers kind of reinforce each other and amplify each other as well. What's happening here, I think, is, you know, if you went back to pre-COVID, you would have gone, you know what, we would have probably had a chip shortage. You know, we are seeing demand in, if you take your car and you think about where the car technology is going with self-driving, you know, autonomous driving vehicles, they have a bunch of sensors in there, from LiDAR to radar to motion sensors, speed sensors, and it all requires a whole bunch of compute. If you look forward to perhaps a premium vehicle in 10 years' time, 20% of the bill of materials of that car may be just semiconductors, right? So you've almost got a, dare I say, a data center on wheels. So that's driving some of the, you know, insatiable demand for semiconductors. What I was going to try and do was link to this and see if this works. Can people see that, or do I need to share my screen?
It's black.
It's black. Okay, let me go back to new share. Hang on. Stop share.
Are you sharing the entire screen or just one application?
I'm just trying to share this, and it will come up now. And this is going to be the video because it was better to do it this way.
So you're about to enter some of the most advanced manufacturing that is done in any industry, any place on earth, right? And the facility here, it's almost $10 billion of investment. every aspect of human existence is becoming more digital. Everything digital needs semiconductors, and that's not slowing down. That's accelerating as we go through this decade. I believe that we were headed for a shortage before COVID, but a little shortage. You know, demand was starting to pick up, more things getting to be digital, and this is a $500 billion industry growing maybe 5% per year. And then COVID. Supply chains go negative, right? Factories are stopped, disrupted in the supply chain. So instead of 5%, we're now negative, and demand skyrockets because everybody is working from home. They're educating from home. They're doing healthcare from home. All of these industries are being increasingly pressured to rise up and become digital more rapidly. This would be a high-end server chip. And this chip, like imagine tonight you go home and you Google something, or you go home and you go onto Amazon, right, to search for something, or maybe you're playing a game online as well. This would be one of the Google, Amazon, Microsoft, any of those, right, servers. This would be the kind of chip. This is the worst that it's ever been for supply. And to build the new factory is years. We're in the worst of it now. Q3 and Q4, I believe this is the worst part that we'll have, and every quarter next year will get incrementally better, but I expect the shortages persist into 2023.
Okay, how did that come across?
It was okay in the end. We've got one question. Do you want to take it now?
Yeah, sure.
Okay, so it's from Diomad. In terms of software and hardware integration, you mentioned, what do you think of Apple's M1 and AWS and Google making their own chips?
Oh, that's a really good question. You know what competition does is it breeds innovation. And if I look at the M1, you've got to say it's a fabulous chip. I've got to be honest, when Pat came in, he's just like, come on, guys, we can do better. This is our core business, right? And that's not to take away anything from Apple. Yes, we see more and more competition, right? Obviously, you have AWS with ARM and Graviton. There's AMD out there. And frankly, I think if I'm giving you the Iain Beckingham opinion now, I think Intel has not executed, and it really needs to get its mojo back into doing what we do really well, which was bringing leading edge products to market. Obviously, if I look at AWS, a significant portion of what they do is on Intel today, and you also have to look at it as there's a whole ecosystem behind Intel as well, right? So there's, as I said, those 20,000 software developers reach out, they talk with ISVs, they talk with operating system vendors. There's a whole base of maturity of workloads that we know run today best on Intel, and we tune and optimize for them. But we're not standing still. We know we've got a competition, and we know we need to do better. We lost the Apple business because we weren't good enough, right? And there's a resurgence now with Pat at the helm to really get our mojo back, and he is changing the company. It's a really exciting time to be. Does that help? Was that a reasonable answer?
We're getting a few more questions come in. Yeah, he says, great answer, thank you.
Okay.
Kitty Hung, will Intel join forces with TSMC to become the global domination of advanced chip manufacturers?
I'm not sure maybe some of the FTCs of the world will let us do that. Just so that people know, we actually part of our strategy is we don't just solely manufacture chips in our own fabs, right? Our own manufacturing facilities. We also use TSMC as well. And actually, it's probably a nice segue once I bring the the presentation back to talk a little bit further about that one, because that really talks to what we call our IDM 2.0 strategy. And are we seeing that now? Am I sharing that?
Yeah, but there's a black bar.
Oh yeah, I will get rid of that one. I think there was some other comments, or I think
there's 3 questions. Do you want to carry on your presentation first?
No, we're taking.
Okay.
I saw the armors cheekily referred to Intel as a niche vendor. Yes, okay, thank you. What is my view of the abandoned merger with NVIDIA? I'm probably not best placed to comment on that one, I'm afraid. And what else was there?
So there's Andrew Stone. How much has the US and Europe's ban on chips from China affected the global supply, and how is Intel stepping up?
Yeah, let me cover that, right? Because that hopefully will take us onto this, and then I can talk around some of the investments that Intel is making. I mean, Pat has been clear that there is you know, a lot of semi manufacturing happens in China, and he would like to rebalance it, right? And I'll come and talk to that, and I will also get rid of this black box. Hopefully here you'll get a bit in the middle, because that says press escape to show floating control meeting options. When Pat came in, he literally within 3 months, it was, we needed strategy, and we're calling it IDM 2.0, right? Intel discrete manufacturing. But what this is around is delivering world-class products, but also having supply resilience at a better cost. So part of what we do is our own internal factory network, right? The nearest fab to, well, I guess we're virtual UK, is actually in Ireland, in Leaslip. So it's just outside Dublin. We have just announced another 12 billion euro investment today. In fact, I couldn't have timed this any better, into Ireland. And I'll talk a little bit more around some of the other investments that we're making in a sec as well. But you know, this is Intel's global factory network, and you know what we do super well is scale manufacturing. We churn out millions of these things per year, right? And I've got a video that kind of shows how you go from the sand to the silicon, and coming up in a little bit. So that's Intel's internal network, and then we've got external foundries. So we are going to use third-party foundry. I mentioned TSMC. There are others out there as well. For those who follow the Intel news, you will all also have seen that we did a $5 billion acquisition of Tower Semiconductors as well. Apparently my internet connection is unstable, which is the black box. Hopefully it will come back. And then the other thing that we are going to be offering is something called Intel Foundry Services. And this is Intel offering a foundry services business to other players out there. And you know, if you look at people that we've signed up for this, it's a world of co-opetition, isn't it, right? You know, but there's people like AWS who have signed up. Other people are looking at this and going, we would like to sign up to Intel because we know that they can manufacture, you know, our semiconductors, because there is this worldwide shortage that Pat alluded to in the video. Let me move on from that, and this is the internal fabs, right? So, you know, geographically all over the world, right? From China, Chengdu, Malaysia, Israel, Ireland, I've spoken about, so that's in Leaslip, Costa Rica, Arizona, Oregon, Dalian as well, right? So that's China as well. If you're following the news, you will also seen around the European Chips Act, the US Chips Act. You know, it's actually hit. In fact, it hit President Biden's speech the other week, right? And talks around some of the investment that Intel is making. If you look at this, when I originally did this slide, we'd cut ground in Arizona for further fabs. That's an investment of $18 billion there. And this stuff is pretty expensive, right? So that's the main picture here is the Arizona. You can kind of see the work behind. If you look behind the main building of the fab, you can kind of see the, I guess, what's essentially a building site, really, of where the new fab's going to be. But that's 18 billion. And then we announced Ohio as well, and this was in the president's address. So, you know, this is 20 billion plus, right? Probably going up to 100 billion investment over 8 years. It's going to generate, you know, thousands and thousands of jobs there as well. So it's really, really big. So that's a big investment into the US. And what you saw today, I don't know if people saw the news, was a 33 billion euro investment into Europe as well, right? So we did announce that we will be building state-of-the-art manufacturing in Magdeburg in Germany, I believe, and then we're having R&D sites in France. We're looking at advanced packaging and assembly. I think also in Italy, Poland, and Spain, if I remember it. And quite honestly, I haven't even had a chance to digest this one because I've been on calls all afternoon. So I was just trying to find out a little bit what happened. So all in all, what you're seeing from Intel is a huge investment into semiconductors and technology. And you've got to bear in mind, you know, when you build one of these plants, it probably takes about 4 years for this to come up to speed. You're looking at, you know, if you probably look at this fab here, and I'm probably guessing a little bit, but I haven't been to that one, but you know, the clean rooms are, you know, sizes of football pitches, you know, times 10 or something, right? That, you know, these things are monumental, and everything about them now is very much robotic, and you know, hopefully we'll see that in the film in a bit. What I wanted to talk through is, you know, some people kind of go, and this is maybe a little bit of an old slide, right? But the question I always get asked is, well, you know, why can't you just manufacture more? Or why can't I have that SKU? And if you kind of work all the way back and you bring in the shipping and everything we do, it probably takes 6 months to go from, okay, we want to start a wafer, right? And as you can see, so we look at what customers want. We then get the raw materials coming in, and these are silicon ingots, and it then goes through the fab, and the video will explain this in a little bit more detail, hopefully. So you add patterns to create the transistors, it's sorted, it's electrical tested, right? We look at, if you look at the green and red, and you know, those are the dyes on the silicon on the wafer there. And some of those are going to be good and some of those are going to be bad. And this is actually where we're using AI now to look and photograph each of those individual dyes and compare them to what they should be. So AI is now really integrated into the manufacturing process. So, you know, we try and increase our yields and learn from perhaps where we're not doing things correctly in the manufacturing space. It then goes off to assembly and test, right? So it's cut, you can see, you take the little square out, you put it on the packaging there. It's then tested, it's then marked, it then gets shipped out. Okay, so the fab sort and manufacturing, so that is in Ireland, assembly test, maybe Costa Rica or something, right? So there's also a ton of logistics stuff that needs to be worked here. Obviously, you know, these things, even though they're probably the size of my, you know, thumbnail or something, there's a ton of money in this kind of stuff. So the other thing that we also need to be fairly careful is how we transport these around the world as well. Okay, let me pause there. Any questions so far? This one's an embedded video, so I'm hoping this is going to work. Okay, so we'll go to the video. This goes into a little bit more detail around how we go from sand to silicon, and a little bit on the manufacturing process. If you ever get a chance to go and see a fab, right, you'll see these things running around the ceiling, right, and they literally go for miles. You know, I think probably 30 miles or so of track. So without further ado, I will hope this works.
The world is producing data at an unprecedented rate, faster than our ability to analyze and understand it. To move, store, and compute all of this data requires incredible processing power. From the blazing speeds of our devices to blazing trails within AI, Intel builds chips that are at the heart of nearly everything. Within every Intel chip manufacturing facility across the globe, innovators are pushing the limits of science and literally rearranging atoms to create groundbreaking technology. This strong silicon foundation is what gives each Intel chip limitless potential. At the heart of all modern electronics, the transistor is a tiny switch, 10,000 times smaller than a human hair, that controls the flow of electrons through a circuit. To build a processor, billions of transistors are packed into an area no larger than a fingernail. It's one of mankind's most complex feats, and a remarkable achievement that Intel has essentially doubled transistor density in every new generation of processors. The process begins when silicon-rich sand is melted and cooled, forming a solid, which is then sliced into wafers. Once inside an Intel fab, the raw wafers begin their long journey through an incredibly complex process. They're loaded into front-opening unified pods, or FOUPs, which travel hundreds of miles along Intel's automated superhighway, going from tool to tool, as processors are painstakingly built up on each wafer. The wafer first goes through a series of important steps, such as photolithography, ion implantation, and etching, that prepare it for the critical transistor formation process. Intel was the first to manufacture three-dimensional transistors called FinFETs. FinFET construction requires first building a channel in the form of a fin. Intel has devised several innovations to overcome fundamental barriers to continued transistor scaling. One such innovation is a breakthrough fabrication method called gate last. It involves building, then removing a temporary gate in order to precisely place the dielectric material and metal gate. This allows for the gate to wrap around the fin and control the flow of electrons through the channel. Another invention moves the transistor contact directly over the active gate. To accomplish this, the gate material is recessed and then filled with insulating dielectric material to prevent the creation of a short circuit. Next, the dielectric near the gate is etched, filled with metal, recessed, and capped to allow a novel self-aligning process that enables the high-density contact geometries. Now, the dielectrics are etched selectively to expose only the desired part to connect to the first metal lines. This is done through an innovative via etch and deposition scheme, allowing contact over active gate to happen. Finally, dozens of layers of metal interconnect lines are added to complete the circuit. After more than 1,000 of these complex steps, the wafers are finally prepared for singulation and packaging. Innovative processor packaging has become a critical feature of advanced computing architecture. 2D and 3D packaging technologies are enabling new device form factors and additional boosts in performance and energy efficiency. Testing of the final product ensures that every chip exceeds our performance and quality standards. In addition to adding more performance and features with each new processor generation, Intel's integrated design and manufacturing capabilities have enabled humanity to innovate game-changing technologies that impact nearly every facet of modern life. Intel keeps powering the world. At the same time, we're powered by you, the makers, the dreamers, the doers, the people who share in our history of making the world smarter, faster, and more connected.
Okay, hopefully that came over okay. I'm just going to stop this one and come out of the presentation. And the bit that I've done wrong is I've kicked it off again. So let me just come out again. You know, I practiced that one and I clearly didn't get it right. Any questions so far on that? By the way, did the video come out over really well, or was
Yes,
it
it was
a bit
okay.
jerky? Or...
We saw it. It was okay.
Okay, good. Any questions?
Yeah, we got a question from WatchTech. It's a bit technical. All this fab talk is very interesting, but
Yeah.
even TSMC is inevitably approaching the limits of physics. Current cutting edge is around 3 to 5 nm with EUV lithography and ASML's 100 million a pop machines. How much further can the physics go, and what's next?
Yeah, okay. Now that's a good question. So, you know, when I joined 25 years ago, everybody said Moore's law is dead, right? We can't go any further. And if you kind of look at the science, we found ways around it. If I look at where Intel's going in terms of manufacturing, we have something Intel 4, Intel 3, and then we go into the Angstrom process, which we're calling Intel 20A. We then go down to 18A, I think, after that. So we still see that we can keep going. Obviously, one of the things that I say, obviously, so some of the things that we will look at is, and it kind of got alluded to, is we looked at FinFET, we looked at metal high K gates, and we're continuing to advance some of those technologies as well, right? And if you're interested in looking at what Intel's doing there was a technology day where you can actually find out a lot more, and it talks in more detail around some of the process improvements, but also some of the packaging improvements, you know, where we're looking at 2D and 3D packaging, like further as well.
Okay, thanks. We've got another question from Andrew. At the quantum level, will observing the quantum chip fundamentally change it?
Can he come off mute and ask it or not?
I think it's more of a philosophical question. Don't know.
Oh, sorry. Let me have a look.
Andrew Stowe, 7:06 p.m.
No, I can't see it. Sorry.
Okay. Vladimir says, what is Intel's transition strategy towards quantum technologies?
Okay, so I mean, at the moment, quantum is definitely in the labs. We do have some qubit operating. It is you know, I know people think probably quantum is the next thing, and it probably is, right? I'm not sure whether I'm going to be around to see quantum. I hope I do, actually. It'd be quite interesting. So yeah, very much in the lab. We've got loads of other stuff in the lab as well. Homomorphic encryption, neuromorphic chips as well that, you know, simulate how the brain works and stuff like that. So if you're interested in where we are, you know, if you look up Intel Labs on the website, you can probably find a little bit more information there as well.
Okay, let's do one more question for now. This is from Mike. How will this disruption of the flow of noble gases and precious metals from Ukraine and Russia affect chip availability in the West?
Yeah, that's a good question, and it's very much top of mind for customers. I know I've had customers see that report as well. Obviously, you know, it's a really tricky situation, and we are doing everything we can to enable and ensure that our supply chain isn't affected by what's happening there.
Okay, we've got more questions, but let's continue with your slides.
Okay, good. I will hopefully share my screen again. Where was it? That one. Okay, share. Okay. And let me get rid of that. Okay, hopefully the black box across the middle will go. Is that clear? Yeah. I wanted to switch gears a little bit because one of the things I wanted to maybe spend a bit of time talking about was sustainability. And when I go and talk to customers, this probably is number one now on their minds, right? Is sustainability. Obviously, everybody's aware of, you know, the climate change. I've, you know, a couple of photos of that one. There's more and more interest and customer expectation as to, well, what is Intel doing, right? How do you make your chips more sustainable, perhaps renewable? You know, I buy a server, I kind of then chuck it away. You know, people do recycle them, by the way. But you know, it's right at the forefront of what, you know, people are concerned around. And then there's this whole circular economy going on, which is, well, you know, you're taking, you know, from the natural resources you make, you consume, you throw it away. How do you change that cycle, right? And have a different economy, right? And you know, people are absolutely concerned around e-waste as well. You know, this is really my mouse is not doing too good today. This has really changed, and I guess the key thing I've noticed is, and it's been, if I went back maybe two, 3 years ago, I might have had the odd question about sustainability. In 20, again, the odd question, but maybe 3 times as much. And then in 2021, it was just a barrage, right? And now it is a top priority for everybody. I think the quote here was, you know, 90% of the S&P 500 index published sustainability reports 10 years ago. That figure was 20%. So again, it's right on people's minds. You know, what I wanted to talk around is, there's a global challenge here, right? And if you look at where carbon exists in the data center use, on the upper left, you see the total amount of electricity used by data centers and the network. This isn't Intel data. It comes from the IEA, which is the International Energy Association, measured in terawatt hours consumed. If you look at the cloud and the hyperscalers, right, so that's the orangey kind of thing and the grey on the left, that makes up the bulk of the energy consumption, right? You know, with traditional on-prem, which is the blue bit, right, making up the delta. The network consumption is projected as a range, right? Actually, so you know, there's a low and a high, and you know, it's the difficulty in assessing the vast networks that deliver data from, you know, various sources and data centers. On the bottom left that you can see is the PUE, right, which is the power usage efficiency of a data center. And it's a key indicator, you know, or it's one of the indicators at least, tell you how well the data center's infrastructure uses the electricity provided to it, right? So basically, the higher the number, the worse, if you're not familiar with this one. And the challenge here, I think you see, is, you know, it was on a nice trajectory downwards, right? And it's really kind of flattened off. And that's a big concern. And, you know, what you then have to look at is the equipment, right? Where the carbon comes from, and embodied carbon, or the, you know, the carbon footprint in manufacturing of servers makes up about 10% of the carbon footprint, while operational carbon, the server in use, makes up 90% of the footprint. So in order to reduce the carbon footprint, we need to continue to reduce our embodied carbon in our manufacturing, clearly, but we also need to enable data center operators to essentially more efficiently use our products. If you kind of, you know, if we got to look at ways to reduce that PUE, and I'll talk around some of the things that Intel is doing and looking at, and maybe you're aware of some of these as well. So sustainable compute is edge to cloud data centers and the network. Often people forget the network bit. Okay, so sustainable priorities for IT. Number one, gain visibility over your carbon consumption. So how much do you know you're using today? Decrease carbon consumption in the existing assets, build next generation sustainable infrastructures. So let's just dive in a little bit more into that as well. So our vision is to take a holistic view of data centers from the edge to the cloud. I kind of mentioned that before. And that puts the network right in between, which is often as big or larger source of carbon than just the servers used to compute. And I think we saw some of that on the other slide. But it does need to be, you know, accounted for in making sustainable decisions on where to place workloads. From there, the vision is to drive continuous innovation around sustainable semiconductor manufacturing. And I'll talk a little bit more on this, right? But obviously it includes the drive to net carbon zero consumption in our product manufacturing. And we're looking at goals on how to do that, using renewable energy to power our manufacturing sites. And I'll talk a little bit more about that, being water positive and zero waste to landfill sites. Sustainable manufacturing then leads to sustainable products, right? We look at the entire system architecture to drive our sustainable product strategy, right? Data centers to platforms to silicon. And then our products, design our products to enable optimizing through sustainability throughout the system. I'm just going to take I'm drying up a little bit, hang on. sponsored by Sports Direct, obviously. So a key innovation in this area is creating modular servers, right? So this is where data centers can, upgrade compute, network, and I/O. This optimizes performance as well, extends the life of products, resulting in less e-waste. And I'll talk a little bit further about that. And then we partner with a broader compute ecosystem to drive sustainable ecosystem as well. And I'll talk a little bit more around some of these areas as well. Some of the bits I had to take out the slide because it was frankly Intel confidential. So I didn't want to have everybody sign an NDA. I think that would have been pretty horrific. Okay, so one of the things, people often go is, well, what is my carbon footprint, Ian? Right? What you can see is we're just trying to put this into a visual context here. So if you look at I don't know where my phone's gone, you get your handheld device, right? This assumes a 3 to 4 year initial life, excludes the networking. This is you're pumping out 50 to 80 kilograms CO2, 160 driven miles. A client, so my laptop, equivalent of 800 miles. The server, the equivalent of 12,000 miles. Now, obviously, it just really depends what some of that kind of stuff is doing, right? As well. If you look at the data center, right, as I mentioned before, embodied carbon is only actually a small proportion, so about 10%. We are committed to reducing those, that carbon through manufacturing goals. And again, I'll talk a little bit more on that one as well. So this is Intel's approach, and honestly, this is not going to be a greenwashing slide, right? This is taken very seriously at Intel. In fact, Barron's did, maybe this is greenwashing, but I apologize, but the #1 most sustainable US company. Actually, I'm proud to work for that company, right? I think it's fantastic. If you look at some of our sustainable manufacturing, so 5% total waste sent from landfills, 7 billion gallons of water conserved, 82% of renewable electricity globally. If you look in the US and if you look in Europe, it's 100% renewable energy. So sustainable manufacturing, sustainable products, so 40% per core, Xeon carbon footprint reduction, energy efficiencies, and then reduction of energy with AI software optimization. So all of this kind of stuff ties together. Let me continue. And so if you look at reducing the operational carbon from cloud to edge, you can split it up into 4 different verticals here. Data center, so you optimize for low power usage efficiency. You can have a disaggregated design. You can use telemetry. You can look at liquid cooling. At the rack level, you can actually increase density. You can use some of the telemetry as well, and you can look at power optimization. At the platform level, you can go modular. You can have the disaggregated servers, you can have different designs as well. And then in the silicon, you can actually increase the utilization. And I'll talk around some of the challenges there as well, because, maybe it's my age, but I certainly came from a world where you would write your software really closely with the hardware. And if I look at, where the software is going these days, it's kind of we can write it, it's very high level. Maybe it doesn't take advantage of some of the underlying hardware as well. But the point here is you can look at workload optimization. You can look at your algorithms. And I think there will be a thing like a green algorithm where you go, you know what, I can do that really more efficiently by taking advantage of some of the features that are inbuilt into the silicon that perhaps weren't available 5 years ago. So how do you architect for sustainability? And, this is really aimed at perhaps a data center. If you think about what a data center does today, you've probably got a big network pipe coming in, right? And you've got some load balancers and some routers, and you've got some networking stuff, and then it hits some general compute, right? And the general compute talks to probably more general compute. Maybe it's, you know, specific for high memory or lower latency or some stuff like that, but you know, maybe that's another Intel CPU. If you look at how you perhaps architect it differently, right, you still have that network coming in, but actually you probably have something called an infrastructure processing unit, looking at the network and going, actually, where does that data really need to be? Does it need to be on CPU? It could absolutely be. It could be general purpose compute. It's a general purpose CPU, off it goes. It could be machine learning and AI services. That could be an XPU. It could be general compute as well. We've actually built a ton of instructions into Xeon that enable you to do AI today. It could be storage, or it could be acceleration services, right? Again, that could be a GPU, that could be an FPGA, that might be a dedicated ASIC, right? So a variety of options. And by thinking about where the workload goes, remember what I was saying on the last slide, enables you to tune and optimize for the right hardware in the data center. And if you look at perhaps a modern hyperscaler data center, this is kind of the architecture more and more that they're looking to put in place. One of the things that people perhaps don't realize is in the processors is the ability to do telemetry. So think of this as a little bit like your Formula One car, right? Where you can look at the engine revs, or actually in your normal car today, you know, you can probably look at this. You can look at how the engine is running, the oil temperature and all of this kind of stuff. You can do exactly the same in a CPU today. And you can look at how hot is it running, what's the utilization, translates to how much power and carbon am I spending and where can I save, what's the load of my data center here compared to over here. You can look at optimization goals, and you can adjust the power and the control to reduce your energy consumption. And Intel enables you to do that. There's a couple of ways by doing that, right? And one of them is the Intel Data Center Manager, which measures the carbon emissions over time. So it takes a variety of inputs into that. So the PUE of the data center, the power consumption of the devices, the carbon intensity, and it looks per data center, per room, per rack, per node, per workload, right? So it can measure all of this. I was going to try and do a demo on it, and then I honestly, I ran out of time. But what you see is very much a graphic of the data center in terms of this is where your power utilization is per server, per node, etc. And it will go red if it's being heavily utilized, and green. You can also look at the heating and all of this kind of stuff. You can then model it. You can set quotas and utilizations. You can set caps and all of this kind of stuff. So that's a tool that really starts to let you understand your data center and how efficiently it's running or not, right? And then you know, if you look at, and my apologies, this is a little bit of a marketing slide here, right? But if you look at some of the cost savings that you do get, right, you get better rack density, you reduce some of those older servers, wasted power and space, and then you optimize your thermals, right? So there's a bunch of stuff that you can immediately start to save money on by looking at things like that, the telemetry that is built in. Let me pause there before I go down into cooling technology. Is there any questions?
Yes. So the question is quantum computing a solution to decrease energy consumption?
I don't think that's the entire answer, no. Right. I honestly don't know how much a quantum computer would utilize in terms of power, right? I think there are other technologies before we get to quantum that, and I'll talk on those a bit in a second, that will be there initially, right? I got to say, honestly, I'm probably out of my depth on the quantum. If somebody can help me there, that's great. But the how much a power quantum computer uses, I don't know.
Okay, we've got some more questions about previous slides. So let's carry on for the time being with the presentation.
Oh, sure. Okay, good. So remember that PUE graph? It was kind of on that downward slope, and it was, you know, tailing off, I think, around 1.5, 1.6. Most of what we're doing in, you know, either PCs, gaming PCs are probably a little bit of an exception, if anybody's got a gaming rig, because they would be liquid cooled. But traditionally, we've used air as the cooling technology, right? So it's pretty easy. You slap a big heat sink on, and you put airflow over it, and it kind of cools the server or the PC. What we know is we can get down to a PUE of about 1.3, 1.2. I know we can go a little bit lower than that if you start, you know, putting it into, for example, I went to a data center in Norway, and it was down an old mine. And because it was so far down the mine, obviously the temperatures were less, right? But that has a cooling effect there. The other one is liquid cooling, right? And, you know, this has been around a while, right? So, you know, two types, you've got immersion and cold plate. Immersion is where you are essentially putting it into a tank of liquid, direct contact with the liquid, and doing the cooling that way. And then the cold plate, but you've then got the risk of leaks, and this is perhaps something that you have in your gaming system today, and that people have. What you can see though is you reduce the PUE down to like 1.03, right? So significant reduction in the cooling. Couple of types of immersion cooling. So you have single phase, you have two phase as well. Global GWP is global warming potential. So some of these use perhaps fluorocarbons, I think, or something that's obviously not necessarily great for the environment. So that's a big consideration as well. But obviously there's a cost, isn't there, right, to going, okay, well, I was air cooled today, and now we're going to have to go to immersion cooling. But what you do see is, you know, a big reduction in cooling energy expenses, reduction in the carbon footprint, and reduction in the cooling and system operation and maintenance costs. And some of the innovative ideas that you will have seen or maybe heard around is actually taking heat out of the data center. And I'm sure I saw one example where they used to heat a swimming pool that was very close by, right? We're also looking at, and I think there's one just outside London where they're looking at data center thermals coming out and providing heating for a neighborhood, right? As and that becomes quite innovative. So there's some innovative solutions coming out in this space as well. If I look at traditionally at servers, a lot of them were underutilized, right? And then they would burst, and then they you get a power blip. But if you look at it in a rack, in a data center, last 10 to 15 years, servers between 3 and 5. Some people maybe go a little bit longer, right? And that is also an answer to the sustainability as well, which is, well, actually, rather than churn your servers every 3 to 5 years, how do you make them go perhaps 7 to 10? So that's today's world. What's coming and some of the technologies that we're looking at are, cluster power optimization, server power controls, and I talked a little bit around some of that kind of stuff with the data center manager, but looking at VM, virtual network function, cloud native functions, power controls within their own rights as well, right? So that's some of the stuff as an insight that we're looking at. The other thing, if you go back to the vision, I talked around kind of modular systems as well. And, these are examples of a one socket disaggregated server. So, you can pop in the CPU, you can disaggregate the IO, you can disaggregate the network card and all of these components. So you're not having to just go, right, let me pull the whole thing out the rack. Right, I can change some of the components and extend the lifetime, and also, maybe as a trivial example, go from 1 gig Ethernet to 10 gig Ethernet, right, and things like that. So here, what you see is you've got a CPU and DRAM module, an accelerator module, and an IO module, right? And on the bottom, you've just got the CPU, DRAM module, and the IO module. Right, so these become separate. So it's just a different way of looking at this. If you look at, and I think this came from Intel itself, right? So clearly we run a number of data centers around the world. You can see the square footage. The worrying trend here is, okay, square footage has gone generally down, right? But the power consumption, look at the power consumption going up 50 to 64 to 85 to 103, right? So, is that something we can keep doing? No, that's something we really need to look at over time. I'm almost at the end, and I'm drying up, lack of water here. One of the things I talked about a little bit earlier was the inefficiencies in software, right? And if there was me at the start, not with quite the 286, but certainly doing some of the assembly, the C, right? Those kind of languages, huge efficiency. When you get to, some of the languages that you get today in the cloud, maybe like the Pythons and stuff, although to be fair, Intel has tuned and optimized Python as well. But what you see is this kind of, there's a gap that's kind of developed, right? And, we probably can do better in terms of writing our code to take advantage of all the things that go into the silicon, and that can be things like vector instructions, matrix instructions, etc. But also just taking to the fact that actually we used to write just for one core, right? And now you pick up a even a laptop, is quad core, it's 16 core, and are we writing to take advantage of all of those cores as well, right? So if you can make your software more efficient, that's going to be a reduction on your carbon footprint as well. The other thing, people need to look at is, and these were a couple of benchmarks that, we kind of pulled together. HammerDB is looking at MySQL performance, right? And then there's WordPress. Over time, right, and let me try and explain what these blue and code names mean, right? So Cascade Lake is our 2nd generation Xeon. Ice Lake, ICX, is our 3rd generation, and you can see the core counts, and the power usage as well. But by moving to the latest generation hardware, and I'm sure you're going, yeah, well, okay, Intel, you're going to say that, right? But you know, do you get greater operational efficiency? Yes. Do you get performance per watt increases and reduce the carbon footprint? Yes, right? And if you went back, you know, maybe 5 years ago, some of the things that you can do today that you take for, you know, you take for granted, frankly, in terms of what the software can do, the fact that you can do AI, you can do, you know, video processing, etc. You couldn't do that a number of generations ago, right? So there are advantages to be had, and that will continue as well moving forward. Here's an example of that. So if you went back and you looked at this is a ResNet, right? So this is AI, and it's inference performance. So this is looking at images, etc. And if you took TensorFlow there and you then optimize it for the Intel optimized TensorFlow, so again, those 20,000 software engineers, this is what the kind of work that they're doing. And then we add deep learning instructions or vector neural net instructions into the processor, you can actually see you get a 10x performance increase, right? So, you know, big gains to be had, not just with the software, but also the software optimizations and the instructions that go into the processors. Another way to look at this as well is and we, if you remember, if we look at that philosophy slide that we had for a data center, right, we talked around accelerators, and I did mention one which was an FPGA, so field programmable grid array. Intel has something called the Agilix, which is brand of FPGA, and this one is doing 5G security encryption, right? So think of this as like an offload engine, right? And look at the power savings that you kind of get when using an FPGA in order to do that. And I won't read out all of those slides, but again, it's trying to change the mindset a little bit from everything runs on the CPU to actually maybe the FPGA does that a lot better than the CPU. It can act as an acceleration service, right? And you can gain savings there as well. My voice is about to go, I think, and hopefully I'm at the end slide. So I've just about made it through, and I will now pause there and come out of the screen sharing, if I may, and take some questions.
Okay, get your breath back a little bit.
Thank you.
Okay, so the first question is from Sheila. How close are you to NVIDIA in terms of competition?
In terms of GPUs or CPUs or AI in general?
I don't know, Sheila, if you want to clarify, then send us another question. It's quite a long time ago, that question.
Okay, let me try and answer it, right? You know, NVIDIA, fantastic company. They've been doing GPUs for a number of years. Again, this is an area that Intel has announced that we are coming to market in. And, you know, from a developer perspective, I think NVIDIA done a great job in looking at AI and CUDA and stuff like that. But you know, I think Intel's philosophy is somewhat different, right? Which is rather than just end up everything on a GPU, it's a horses for courses, right? So we have, and what I showed last time we were face to face is we have AI in a drone, so it's a visual processing unit. I can't put a GPU into a drone, not easily, right? And it could come down, it could fly down, and it could detect my hand, right? So again, it's thinking about those workloads. You know, there's data center workloads, but there's also intelligence at the edge of the network, which is something that perhaps doesn't require a fully blown GPU, right? Perhaps it does need inferencing. So it's looking at images. Think of it as a smart city, looking at, you know, people images and stuff like that. You perhaps don't want a huge power draw, or you have different requirements. And this is where, you know, I think Intel does have an advantage because it has a very balanced portfolio. Okay, but that's not to take anything away from NVIDIA. As I said, they've got some fantastic products in the market there as well.
Okay, this question is from quite a while ago as well. So Chris asked, why is the SFM in a different location? Is this just to lower labor costs? Would you not be able to automate it?
The SFM, sorry.
FSM.
FSM.
I think it was when you looked at the map.
Sorry. Yeah, that's fabric, the sort stuff. I think it was that slide, was it?
I'm not sure.
Let me look. Hang on. Yeah, okay, so the manufacturing. So manufacturing in Oregon, Arizona, New Mexico, Ireland, Israel, Dalian, and Germany to be built. Sorry, what was the question? Are they high cost?
Why are they in a different location? Is it just because of the labor costs, or can you not automate it?
Why are they in a different location?
Is
You know,
it redundancy or something?
Well, so I guess the question could be, why do you not have everything in the US, right? And I think part of the answer to that is, you know, Intel has a global presence, right? It invests a lot into, you know, all of these countries, right? If you look at Ireland as an example, I can't remember how much as a percentage of GDP we are, but if you look at the investment that we've had there over 30 years, it employs thousands and thousands of people, and it's the knock-on effect there. So, you know, I'm not sure it's great to have everything in one place, right? Frankly, I think that could equally cause us challenges.
Thanks. The next question is from Anthony. As you mentioned, Intel dropped the ball, so to speak, with Apple going it alone. How far ahead of Intel would you say they are with their latest M1 Ultra technology?
You know, I think what you're seeing from Intel is, if you look at our 12th generation core, it's something actually very similar in terms of the architecture. For those who aren't familiar with it, the idea is that you have performance cores and efficiency cores, right? So two different types of approach there, right? So, you know, if you're doing something compute intensive, you're able to move those threads over to the performance cores. And if you're doing something less compute intensive, they move to the power efficiency cores, right? So I kind of looking at, you know, M1 really good. I think Intel's catching up, right? And, you know, I know what the roadmap plans are, right? And, you know, I'm hoping at some point in, you know, Apple turn around and go, well done, Intel, you caught up, and actually you've taken over the performance mantle again. Remember, I guess the other difference between the two is for Apple, it's just that is their ecosystem, it's their apps, it's everything they do. For Intel, obviously there's everything from Linux to Microsoft to Chrome and stuff in between as well, right? So a lot more validation needed. And you know, potentially that's I'm trying to be balanced here. That's an advantage there for Apple as well. They know what they can control in their garden, tune and optimize it as well.
Okay, thanks. The next question is from Nobby. Is Intel planning to get into MEMS, MEMS?
I don't know. I've got to answer that one truthfully.
Okay.
Is that the MEMS? No, hang on. Yes. Okay. I know what he means now. Yeah, we have looked at that actually previously. It's, you know, are we going to do MEMS as an IoT sensor? Probably not, right? But built into microprocessors, yeah, that has something we have looked at previously.
Okay, I can see in the chat, Chris has clarified his previous question. So the question, he says the question was, why fab in one location, then ship somewhere like Costa Rica to complete the process? Would it not be possible to automate it and do it in the one place?
Okay. Yeah, it would be. You know, I kind of looked at that one as well and went, gosh, you know, isn't it really bad of us that we manufacture here and then we, you know, ship it halfway around the world for assembly, test and build, right, before going out? I honestly don't know the answer to it, right? It's a really good question. I might go and ask that one.
Okay, Andy asks, what is the cause of the current memory chip shortage?
That's a good question. The and it's not just memory chips that are short as well. If you look at the components that go into a server, there's PMICs, which are power management ICs. There's a whole bunch of these things, right, that are not just memory or the CPU or the chipset, right? Everything, you know, from audio codecs to a whole bunch of stuff in between, and ultimately what some of the shortages around that is there's a supply and demand gap, which I think Pat answered in the original video, which is, you know, we had a gap and then, you know, COVID hit and guess what, demand soared through the roof. So we can't manufacture enough of the stuff, you know, literally the factories are full and we're having to make very careful decisions as to what products we manufacture. But some of that is down to a shortage of substrate as well, right? And certainly from the chip perspective, that is something that has driven the shortage, and that's a global shortage, right? That affects everybody, not just Intel.
Okay, I've had a clarification from Nobby. When he said MEMS, that means micro electromechanical systems.
Yeah,
okay.
Correct. Yeah.
All right. Okay, we've got time for one more question now. So this question is from Tim, and this was when you were showing us the slides with the programming languages. So he says, what kind of language compiler research effort is Intel putting in to help us close the gap in performance?
Yeah, but so good question. So there's a couple of things that Intel's doing. If you didn't know, Intel actually has a compiler team, right? So we have our own C++, Fortran compilers. Back to the telemetry in the chips, we have tools which are called VTune that enables you to profile your code, to look at which registers are being hit down to the cache level. You know, is it a cache hit, cache miss? You can look at all of that information. You can look at where the bottlenecks are, and so that's some of the tools that we have. We then also work with. So there is a, you know, I mentioned Python. There's an Intel optimized version of the Python where we tune a lot of the libraries. We also write our something called the mass kernel library, and that, again, that is tuned and optimized to take advantage of like vector instruction sets. So you can do blasts and fast Fourier transforms and stuff like that. And all of this comes together in something that we're calling one API. Right, so if you go and look at the One API initiative, and what we're doing, you'll see there's a bunch of stuff that we're looking at in terms of developer tools, compilers, and making sure that they and generally the idea here is, you know, you kind of I don't necessarily want to pitch this, right, but the idea would be, write your code, system goes, actually, is this going to be work better on a GPU or an FPGA or CPU? Actually, you don't care because you've written in it such a way that it figures that kind of stuff out for you. It's a very simplistic way of looking at it, right? It's a little bit more complicated than that.
Okay, well, thanks a lot. We've got to the end of the questions now. So I'm going to hand over to Dalim to give his closing remarks.
Yeah, well, you have done really well, Ian. Your voice has lasted out. You've displayed your very wide and deep knowledge of your subject, I must say. You're very much an Intel advert. The sign behind you on the wall is writ large, and you've displayed a lot of aspects of what goes on in this fascinating company. So again, thank you very much, Ian, for sharing your knowledge with us, and we look forward to seeing you next time.
Yeah, thanks.
All the best, everyone.
Yeah, thanks, Dalim, and thanks everybody for attending. If you want to reach out to me, it's Iain, Iain .beckingham@intel.com. Happy to take any further questions there. Yeah, no, really appreciate it and love the interactivity. Thank you, Dalim. Lovely to see you. And thanks to the BCS team. Right, really appreciate the opportunity.
Great. That's Iain. That's
I'll put it in the chat.
Yep. Beckingham@intel.com. Yeah.
Yeah. Yeah. I'll stick it in the chat and then people can see it.
Great. Thank you, Iain, and thank you, everybody, and especially for your great questions too.
I'm just giving people a chance to see the address.
Yeah.
Okay, goodbye, everybody.
Great. And thank you very much, David.
Thank you.